Good morning. We are the Plate Swapper team. I'm Dan Williams, mechanical engineer.
I'm Taylor Dolan, mechanical engineer.
I'm Mara Adams, mechanical engineer.
I'm Jocelyn Gazzardi, electrical engineer.
So what is the plate swapper? The plate swapper is exactly what the name details. It swaps plates for a 3D printer. The problem that we were coming on was the fact that you can't print multiple parts in one setting. So we created a robotic solution for less downtime for printing overnight and increased batch production. This is our design from last semester. You can see there's multiple 3D parts that we designed, as well as 2040 aluminum extrusion and multiple different linear rods.
So at the end of last semester, as you just saw, we designed a 3-component system with a spring stack, gantry, and a drop-in gun with plans to design something to catch the build plates. So due to time constraints, we decided to remove the spring stack from our scope, so we're only swapping one build plate. This also removed our need for a plate retrieval system. Additionally, we changed our gantry design so that the top grabber is passive while the bottom grabber moves using both motors.
Within the scope of our project is removing and replacing the build plate. Also within the scope of our project is using 120 AC voltage to power our device. It is for an open-air bed slinger style 3D printer. Outside of the scope of this project is forking a slicer, setting up serial communication between the printer and the robot, and sorting the build plates.
So in January and February, we were focused on procuring our materials as well as working on our PCB and testing that. And we also made sure to print our bigger parts for our 3D printed designs because that was important. In February and March, we focused on reprinting these parts because we were having issues with the tolerances and the hardware. And then we were also focusing more on soldering our components to our PCB as well as testing them. And then in March and April, we had some issues with our stability and alignment, so we were focused on fixing those, and then we started our testing for durability. We started testing our code, and then we started testing the temperatures of our electrical components.
Okay, so I'm going to be discussing a few of the main electrical design challenges that we encountered in this project. First of all would be the PCB design. This involved lots of different revisions, and also there was a bunch of research I had to do on the aspects of PCB design, what I needed to include, how to use the design software. So after going through many different, these were software-based revisions, we ended up getting a good physical version of that for our project. We also ended up getting issues with electromagnetic interference due to our motors. So because we have a bunch of limit switches in our design, the electromagnetic field from the motors was causing us to be getting false high signals to our microcontroller during operation. So we rewired these limit switches with a 4-conductor shielded cable, which was able to eliminate that issue. And then we also had some issues with temperature. In particular, there was one capacitor in our regulator circuit that was getting pretty hot, around 90 degrees Celsius. It's still below the rated value for that capacitor. However, we wanted to improve this. I do think that that issue was likely because of rapid charging and discharging because we're running the stepper motors. But we added in a couple of cooling fans to our box to create a nice draft, which ended up cooling down the temperatures. Here's just an image of the updated PCB schematic. You can see in the upper left-hand corner are our motor drivers with capacitors across them. Here's our microcontroller. Here's our regulator circuit. Here's the connectors on the side of the board to connect everything to all of our sensors from the outside world, as well as our LEDs. You may notice that we have removed the relays that we originally had in our design. That's because I wanted to keep the PCB size the same, but also increase the trace width of the paths in the PCB in order to be completely sure that we have enough amperage in the board. That took up some extra space, but we wanted to keep it at 2 layers, so I ended up eliminating that. But I would have liked to have added it back if I could go back, because it would have protected us from the back EMF. So here's the software-based image of our PCB design. You can see all of our trace paths and everything here, where everything is Here's an image of the actual PCB in our electrical box. You can see all the wires coming in right here into our box and then connecting to our connectors over here on the side, as well as this copper tape that's outlining the inside of the box. That's connected to our negative DC and serves as extra shielding for our robot. So here's just another image showing that, as well as our lid, which is also shielded, and we have the two fans connected here, as well as our power supply, which, if I haven't mentioned, is a 24-volt DC power supply, and it plugs into our regular 120 volts AC. And then here's just the outside of our box, as well as our emergency stop button.
So we produced a lot of 3D printed parts for this project, some due to the unpredictable tolerances of the 3D printer, and some due to rigidity concerns for our frame.
So during the building process, as Daniel mentioned, we were having stability issues, so we also added the rigid frame, which helps stabilize our gantry, and we added a second motor in the horizontal direction because the gantry would lag on the side without the motor. So we added these and a bunch of them to 40 and fixed most of our stability and alignment issues.
Okay, so regarding the addition of the linear motor on the electrical side of things, in order to add this, I took the original motor, I spliced into the cable, and just soldered the new motor in parallel with that motor. This does split the current from the motor driver between the two motors, but we did have plenty of current and sufficient torque, and this was able to fix the misalignment issue that we had. So regarding the electronic temperature issues, adding the fans significantly improved the temperatures of our components, and I took measurements of those average temperatures. So our average driver temperature was 35 degrees Celsius. Our regulator circuit capacitor, which is the one that we were struggling with temperature issues, was now about 50 degrees Celsius. Our other capacitors at 25 degrees Celsius, as well as our regulator chip, and then our microcontroller was about 32 degrees Celsius. So regarding the coding, this program was written in C++. It's primarily a series of while loops because those are great for running stepper motors. It's divided into two separate main functions, which one is for the homing and one is for the whole plate swapping sequence. As you can see, that was an example of one of these while loops. We've included things like our limit switch signals until it went to stop, as well as these counters, which is such as NH3 here, which is an integer value that counts up as the motor steps to make sure that if we miss the limit switch, it won't keep going forever, it will eventually stop.
So here's a photo of our prototype as well as our physical prototype. It's about 25 inches long, 15 inches deep, and about a foot in height. Limit switches is what we use for our input signal for our microprocessor. It starts as soon as a print is done. The 3D printer will touch a limit switch that starts our entire system. The gantry system then moves to the beginning or to the printer, and it will retrieve that plate, bring it back, drop it, retrieve another plate, and then place it onto the printer we'll just place it back onto the printer.
So after we finished our initial prototype build, we first started testing limit switches because the system needs to know where it is in order to execute all of its functions. Then we moved on to testing the code execution to make sure it tells us before placing it next to the printer. Then we just ran the system and made sure that it hit all of our requirements and specifications, which we'll go over in a bit. And lastly, we did maximum load testing, which we'll also see a video of. And then for testing purposes, we manually input this G code to move the bed of the printer, which you'll see in the video. In real life, this would be coded ahead of time with the node place.
So requirements for success. Number one, we must remove the completed build plate with the object off of the printer. Two, we must remove it out of our gantry's grabber setup and safely drop it to the floor in the designated location. Three, we must load a clean build plate onto the printer, plus minus 5 millimeters from the sides.
So here's a video of our process working. You can see in the beginning it goes up, touches the first limit switch, and then approaches the printer. This is sped up in 20 times speed because the entire process takes about 14 minutes just for safety. So it goes, picks up the plate, and then drops it in between the two build plates. And then it then goes back, picks it up the same way that it did before, and then brings it towards the printer. This then drops it within a 5mm tolerance. And then this is just it homing.
Okay, so regarding the electrical power, we measured our AC current and also our real power for this design in the 3 different modes of operation, including the resting state with the linear arm moving and then also with the grabber moving. So you can see the AC current listed above as well as the power. The power in the resting state was 13.6 watts. The power with the linear arm moving, 25 watts, and 42 watts with the grabber moving. This gives us an average of about 30 watts during the swapping operation.
This is our max plate load test. We loaded it until failure. We were able to successfully lift 400 grams off the build plate. For average comparison, that's about anywhere from 2 to 8 times as much mass as we would normally put on a printer of this size.
So since the plate swapper is able to drag those plates off the printer that are heavier than what it could actually lift, we decided to see how much it could lift if the center of mass of the print was moved closer to the edge of the build plate. So 15 millimeters would allow us to lift about 460 grams worth of filament. More realistically, you wouldn't have it that close to the edge if you're printing a more massive print. So 30 millimeters would allow us to lift about 230 grams. Overall, our testing showed that we could successfully take 400 grams off worth of filament off of the printer. Along with the 200-gram build plate, we were able to place the new build plate within the 5mm tolerance, and our test system runs in about 14 minutes, including the homing time.
So for ethical and safety consideration, we treat the NSPE Code of Ethics, Section 1, Subsection 1, we hold paramount the safety, health, and welfare of the public. For our safety concerns, we decided to make sure that the PCB is in a box, all wires are covered, there's an emergency stop provided on the electrical box, as well as the maximum allowable steps in our code.
This is our schedule. We were right on time for all of our tasks.
For our budget, we used $307.15 of the Wilkes budget. We also provided different equipment ourselves, which still left us a little bit over $70 under a $500 budget. In the real world, it would cost about $64,879.72 to mass produce 100 units. This is also including engineering time as well as the 8-hour per machine to build. And this brings our cost per unit to $347.85, but this is still grossly overestimated because we're still using suppliers like Amazon and not buying things in bulk.
So what we learned that the cantilever design was just way too flexible, so we ditched it in favor of a more rigid design. We also learned that 1 motor per axis was not the way to go, so we put 2 motors per axis. We shielded our cables for the limit switches so we got more consistent signals, and we put WD-40 on every bearing.
So during the 13 weeks we had to build and test our system, we accomplished a lot of what we set out to do, but obviously if we had more time, we were going to improve. First of which is adding the spring stack, so we could hold 3 more build plates instead of just the 1. We would maybe have opted for a belt system as a lead screw system to speed up the process, but that would require more design time. We would have added an enclosement, wire runners, and wire connectors to improve the appearance. And lastly, if we wanted to open source the project, we would write a manual for each of these to build. But however, we're very pleased with our success given the time constraints. We were able to accomplish all of our requirements and specifications. And although we didn't swap 3 build plates like we initially set out to do last semester, swapping the 1 build plate still gives you several more hours of printing time if you're not ready. Overall, this was a very good learning experience for all of us.
Okay, we would like to thank Dr. Anaya, Mrs. Staff, Mitch, Dr. Garishi, Dr. Zhu, our peers, Dr. Bednars, and all the other professors for all of their helpful feedback and assistance in this project.
Thank you. Any questions?
You got it? I know you got something.
No, I'm not going to make you suffer with software. Question I had is just talk about testing. And you made on your one chart, you showed requirements and specs. Did you create a test plan that did testing versus your requirements so that you could document and say, yes, this requirement was satisfied, this was satisfied? Because I didn't see that presented in the slide.
So originally on our requirements and specs, last semester we wanted to do 3. Once we realized we didn't have enough time for the spring stack, when we submitted our revised edition, we included 1 test run, successfully removing a build plate with a completed object and returning a new build plate.
Okay, so those are what I had listed down. You had 3 primary tests that you performed and requirements that you didn't make, but there was other requirements that were associated to it. So you had when you did your original design plan, you came up with design requirements. And so as part of the systems engineering approach, you should be taking design requirements and turning them into, here's the test plan to take and say, yes, I've satisfied that requirement or not. And so you satisfied the 3 major high-level requirements, but did you satisfy all the lower-level requirements?
Yes, in the beginning of last semester, we had to give Dr. Bednar's a report of basically all of our specifications and requirements of our entire project, and we had to revise it at the end of last semester and this semester, and we have met all of them.
Good answer, thank you.
Good job. My question is regarding alignment. So you mentioned the value that you achieved. Can we decrease that value, or do you think the value that you got is going to be good enough? And the second question is in terms of implementation. There is like any limitation regarding the 3D printer that we can use, or is something that we can apply to different kind of 3D printers?
Okay, so regarding the misalignment issue, we were able to fix that, and we haven't, we didn't run it a large amount of times to watch the error accumulate, but at least running it a few times, we don't see any significant change in the alignment. So it does do a good job of staying aligned. And then the other question, limitations. Yeah, so we designed this to work with Bedslinger 3D printers, so that was our the only part of this that we intended to be for.
All right. Thank you so much. Okay, very good job. I'm biased, of course. I've been seeing you for 2 semesters, but to be honest, I couldn't take any credit for what you guys have accomplished. So, but I do have a few it's good things I want to mention, which is everybody sees what happens when you put a group of good engineers together. This is the hope of engineering. So, but I do want to comment on, especially the subtle details, which is we always say devils are the details, right? So sometimes, especially when you design engineering system, the kind of care you took when it comes to the temperature of the system, that's a tremendous amount of care you took, which is because that says a lot about your design. If things overheat, it just that normally when you come here, people can simply just put that underneath their rock and just try to even just run the system for 2 minutes, but you actually took great care and try to expose the weakness of the system, try to take care of that. So that's a great. The second thing I would like to really comment on, which is the care you took for the PCB design. You can just absolutely just put a massive graphical system there, but yes, everything is a learning process, but at the same time, again, it's about the devils are in the details, because when you are an engineer, most of the time, nobody tell you what to do. It's you are driving yourself. You push yourself to your highest potential. You are trying to, when you are doing the best you are doing, you don't feel the pressure from your team, from your boss, from your company, from your customers. So that's my advice to all the engineers, to all the students here, which is that when you see an issue in your system, don't try to put it underneath the rock. Try to face it, try to overcome. That's the right mentality, which is crucial. Okay, so for those 2 things are really, third thing, which is the kind of how careful you are if the system, this plan doesn't work, how quickly you can adapt and try to come up with a new plan. Like if one motor is not working so well, 2 motors, and change the design, and how you even do the trial and error regarding your mechanical design doesn't work, and how quickly you can adapt and try to, those are all great engineering skills. So I'm seeing lots of good things, but if you see, I don't do this much. I try to be critical, but at the same time, when I feel I'm very impressed, I do see that, and I just want to see you guys did a wonderful job. Great care took in this project, so very good job. Okay, thank you.
Any other questions? I just want to quickly echo what Dr. Su said. Watching your struggles and the evolution of this project, 3 last presentations last semester, the end of the semester presentation, 3 more, so this is the 8th time. Myself, all your peers, Terry, who are watching you. When you show the working video, Terry and I kind of literally look at each other and smile. We're excited for you that you accomplished what you set out to, so great job.
Did you ever use that emergency button?
We do have emergency stuff.
What happened? What happened? What are the scenarios when you have to use it?
Sorry, what happened to me?
Yeah, when did you have to use it?
Well, we haven't used it for emergency, but it's between the power and the motors. So it will power.
Was it an emergency?
No, we haven't had an emergency.
Okay, so but you never kind of true emergency, so that's okay. So is there any auto stop feature at the end of the day, if something goes wrong, just have stop the system? Did that ever happen
Well, when we were first originally testing, we would sometimes if the limit switch wasn't properly hit. So that we would get the signal, it would just keep going. We do have in our while loops integers that count the number of steps that prevent it from overstepping, so that it'll eventually just stop.
So in the software, there is a feature to see shut off the entire system.
Yes.
So what's that signal?
So it's just a counter in our while loops that will stop it. And in our homing code, we also have a while loop where it will go and it will start flashing an LED to say that there's an error. So that we'll be able to detect that.
Okay. All right. Thank you.
Any other questions? Okay, great job. Thank you.